God morgen og velkommen alle sammen til vår webinarserie God forskermorgen. Dette webinarserie er organisert i samarbeid av Multiconsult og Hydrosen, og en gang i måned kommer en forsker fra Hydrosen og presenterer sin arbeid til oss i bransjen. Jeg heter Filip Patočka, jobber i vannkraftseksjonen av Multiconsult, og har glede å invitere Kristian Sagmo og dele sin forskning på blade trailing edge modifications for increased longevity of turbines in flexible operation. The presentation is in English. If you will have any questions, please write them to the chat and we take them afterwards. And the webinar is recorded. Go ahead, Christian.
Okay. Thank you, Philip. I hope everyone can hear me okay. So hi and welcome again. As Philip mentioned, my name is Kristian Sagmo, and I'm a postdoc at the Water Power Laboratory at NTNU. I'll be talking a bit today about blade trailing edge modifications for increased longevity of turbines in flexible operation. Now things will get a little bit technical towards the end, but I hope that you can bear with me and that you have your cup of coffee or favorite type of beverage with you, and yeah, we can get into it. So in the meeting invitation, we introduced the topic and noted that one of the challenges related to flexibility of operation is increased risk of vortex shedding induced vibrations at the trailing edges of blades in the turbines and leading to fatigue and cracking. So the question was, is there a straightforward design modification that can be utilized to mitigate this risk? So in order to provide some motivation and eventually attempt to answer to the opening question, we'll be going through some of the central topics and terms, such as what is trailing edge vortex shedding and vortex-induced vibrations, the challenges for flexible operation and longevity, and then result from the research and the proposed solutions. And I'll mention that the results I'll be presenting today is previous work from my PhD thesis that me and my colleague and previous supervisor, Paul-Tore Storli, we recently published in the Journal of Sound and Vibration. And you can find much more details on the topic in this paper. Also, some of you may have seen parts of this work in previous presentations by either me or Paul-Tore, but hopefully it will be new to most of you. So vortex shedding, I think, is something most of us have an idea of what is. Some of you may have seen vortex shedding behind bridge pillars in a river, for example, or other areas. Here's a nice image, satellite image taken by NASA in 1999. What you see here is an example of large-scale vortices being shed from an island visualized by cloud formations. Vortex shedding happens at both large and small scales, and is also present in the wake of turbine blades. Here you see an example of vortex shedding behind the hydrofoil, as visualized by a degree of vorticity in a detached eddy simulation. Now, many of you will know that there's a relatively simple linear relationship between the frequency of the vortex shedding and the velocity surrounding the fluid over an object, as described by the Stroll relation. In practice, though, pinpointing vortex shedding frequencies from a hydrofoil or a turbine blade is not necessarily so straightforward. Here's an example of results from the previously shown geometry from computer simulations with different turbulence models compared to experimental results here in black box. Now we can see that the difference between the estimates can vary quite a bit, and it's not unreasonable to account for a 50% error margin when estimating vortex shedding frequencies. So why do we care about vortex shedding and its frequency in turbines? Vortex shedding can become a problem when we get vortex-induced vibrations, particularly at resonance. So resonance conditions occur when the natural frequency of the blade itself, here denoted Fn, which is associated with a specific bending mode, becomes the same as the vortex shedding frequency. Here is some data showing you what this typically looks like in practice for a turbine blade or a hydrofoil. In this plot, we have the frequency measured on the left-hand axis. And we have the blade's vibrational amplitude indicated on the right-hand axis, plotted in triangles. So we observe that as we increase the channel flow velocity, we have a linear increase in the measured vortex shedding frequency. And while the natural frequency of the foil in yellow markers here stays roughly constant. So when the two frequencies coincide, we get a large increase in the vibrational amplitudes. And this range is where the natural frequency of the foil and the frequency of the vortex shedding overlap is referred to as the resonance range or lock-in state of the vortex-induced vibrations. So these vibrations can be quite violent and loud, and will shorten the lifetime of the blade through fatigue, or in some cases lead to direct failure in certain conditions. So I was going to play back a recording from the lab here for you, but I'll just skip this because we had some issues with the sound, and to be frank, I don't think that the sound will be too pleasant. It's quite noisy. So I'll just skip this for now. But going back to explaining why vortex-induced vibrations can be a challenge for flexible operation and the longevity of a turbine. So normally, a turbine designer can separate out the vortex shedding frequencies from the natural frequencies of the blades in the turbine by careful design. But for more flexible operation, this becomes more challenging. So as we know, there are many blades in a Francis turbine. We have the stay vanes, for instance, the guide vanes, the runner blades, and maybe you even have splitter blades. And depending on how flexible we would want the turbine to run, it may not be practically feasible to ensure that resonance does not occur under any of the operating conditions. So just to give you a sense of what the flow may look like for different load conditions in a Francis turbine, we have some velocity measurements in the vanes space of the Tocke model here in our lab. So we'll see here is the measurement location indicated by the white square behind the guide vanes. We have the velocity, and we can see the wake of the guide vane marked in purple downstream of the guide vane. And the vortex shedding indicated by the vorticity in the flow. So here's the average flow field velocities measured for different load conditions or operating points of the turbine. We have a deep part load, high load, and full load for different guide vane angles. And as you can see here, the velocity field can vary quite a bit for different operating conditions. And avoiding any overlap of the vortex shedding and the natural frequency of the blades, not necessarily the guide vanes, but other blades in the turbine, can become increasingly difficult as you add more operating points to your run schedule. So in addition to the complexity of flexible operation, trailing edge vortex shedding in a turbine can also change as erosion or cavitation slightly changes the trailing edge shapes of the vanes and the blades in the turbine. And so issues with vortex-induced vibrations is something that can occur over time. So back to the question, is there a straightforward design modification that can be utilized to mitigate the risk of vortex-induced vibration resonance for turbine blades? Hopefully by now you have become convinced that this is a research question that is worth seeking an answer to. So the research proposal that we have experimented with in the water power laboratory at NTNU involves the idea of introducing semi-stable streamwise vortices to break up the vortex shedding coherence along the span of the trailing edge of the blades. By doing so, we hope to provide a softening effect on the trailing edge pressure fluctuations. Here you see the different trailing edge geometries that we have tested. So if we have a trailing edge geometry fitted with vortex generators, and a trailing edge with serrations or undulations. And of course, in addition, we have a reference trailing edge to compare results with. Here you have some images of what the implementation of the foil and exchangeable trailing edges looked like in the laboratory. You can also see the location of the embedded strain gauges used to measure the resulting vibrations of the foil, which we'll get back to. Here's just to show you some images of what the calibration of the camera and laser we used for the velocity measurements looked like. I will not go into the details of this type of measurement technique, but it is a way of using microparticles in the water that you can track by taking images and then calculate their movements, thereby providing a measurement of the flow field. Here is an illustration in order to give you an impression of what we hope to achieve with the different designs. So this is a bird's eye view of the trailing edge with vortex generators. The mean flow direction is from the left going to the right. The vortex generators, they set up streamwise vortices, meaning vortices are aligned with the flow. And on the right here, we have the mean velocity field measured in the transverse direction or up on the page. We see that this flow component goes from negative to positive in a predictable pattern corresponding to the streamwise vortices introduced by vortex generators. So this is kind of what we hope to achieve. Now, for the serrations, we have a similar condition with the curved separation line along the trailing edge, introducing streamwise vorticity into the flow. And the resulting flow field as predicted, follows a cyclical pattern, going from negative to positive, and so on. In other words, both of the geometries that we have tested alters the flow field by introducing this streamwise vorticity into the flow, which we wanted in order to break up the more regular type of vortex shedding that we get from a straight or slightly curved trailing edge. So let's see. Over to the main results from the measurements. Here we have the vibrational response from the reference trailing edge, similar to the plot that I showed you earlier. We can see everything behaving as expected with the vortex shedding frequency, again increasing linearly until it coincides with the natural frequency of the foil. And then we have resonance. I should point out that for this plot, the scale of the relative vibrational amplitudes on this right-hand axis is on a logarithmic scale. This means that there is quite a large difference between the amplitudes at resonance and outside of resonance, even though it might not look like it. So looking at the results for the vortex generators, we see that even at resonance conditions, we have vibrational amplitudes that are only about 20% of the levels compared to the reference. So here we're actually talking about a 80% reduction in the vibrations of the foil, which I think is quite an exciting result. When we look at the results for the serrations, however, we see a shift of the resonance range towards higher or larger flow velocities. This is somewhat expected, but what is not so expected or somewhat surprising is that we have the elongation of the resonance range here. You can see that the overlap between the natural frequency and the vortex shedding is much larger for the serrations than it is for both of the other cases. So I should mention that some of the increased vibrations that we can see here for the serrations is explained by the fact that we have a more energetic flow, I mean higher flow velocities, what means more energy in the flow. And the fact that the foil stiffness, as seen from the view of the strain gauge, is somewhat weakened because we have cut into the body itself. But still, this is a somewhat surprising result. So in order to gain further evidence here for what is going on, we looked at the correlation of the streamwise velocity fluctuations in the wake of the hydrofoil. Here again, we are looking at the flow directly downstream of the trailing edge, the serrated trailing edge in this case. So yeah, here things get a little bit technical, but you can think of this plot as a map that gives us the degree of connectivity or coherence of the velocity fluctuations in the field or space across time with respect to a specified point. Let's see here in marked in red. And yeah, any type of periodic behavior in this plot will show up as a pattern. Now for the vortex shedding, which is a periodic behavior, we can, for example, extract the frequency by looking at the spacing between the coherence peaks. Normally, for a straight trailing edge, we would expect to see elongated lines here of coherence running vertically and parallel to the trailing edge. Instead, what we observe is just some very faint correlation peaks running along the spanwise direction, which is precisely what we hope to achieve and what was intended for this design. Now I should point out that these results are for free stream velocities below resonance conditions. So what happens as we approach resonance? When we increase the bulk velocity over the foil and approach resonance, then we start to see a more coherent pattern for this design along the span of the blade. So in principle, this means that the design is not that efficient at decorrelating the velocity fluctuations under resonance conditions. It seems like the vibrations are overpowering and actually altering the flow field to a significant degree. When we look at the correlation map for trailing edge with the vortex generators, we can still pick up an underlying vortex shedding frequency. But there is no coherence pattern running along the spanwise direction or the vertical direction in this plot. Instead, we see the correlation running along with the flow, which is indicative of the relatively strong streamwise vortices that are originating at the vortex generators themselves. And then finally, when we look at the results for the vortex generators at increased flow velocities, so this is very close to resonance conditions, we still see no apparent correlation along the span of the blade. So this means that the vortex generators are effective at decorrelating the vortex shedding also during resonance conditions, which is, again, is an exciting result. So finally, to include, if we ask again, is there a straightforward design modification that can be utilized to mitigate the risk of vortex-induced vibration resonance for turbine blades? We can say, yeah, it does appear so. What seems to be the condition is that vortex-induced vibrations at resonance can be mitigated to a large extent. Here we've seen an example where we have an 80% reduction in amplitude at resonance, provided that the streamwise vorticity is introduced sufficiently far upstream of the main separation line at the trailing edge. Now this is an important step towards providing a passive flow control solution for the industry. That can be utilized both for new designs and retrofitting. I'm not claiming that you should use vortex generators necessarily, but there are other designs that can achieve the same principle and the same physical flow field. And what's exciting to us is that these fundamental results also have an impact far beyond hydropower turbines. So you could use these results or this principle in gas turbines and hydrofoils in ship design, in marine propellers, offshore risers, and more fields. So that concludes my presentation. I would like to thank you for listening. I hope it was at least somewhat interesting. And if you would like to know more, then again, you can find further details in our recently published paper, or you could reach out to me. And yeah, any questions?
Thank you very much, Christian. It will be interesting to hear if there are any questions. I know that there is quite a few mechanical engineers in the meeting. You can either write your questions in the chat or raise your hand, and then I can allow your microphone. Very quiet for the moment. Did you manage, Christian, to either do the implementation itself or get a turbine manufacturer to test actually on site on a full-scale hydropower turbine?
Yeah, so that would be the logical next step here. So this is kind of the first stepping stone, because obviously we want to make sure that we have some sort of solution before we actually go and test this, take time to test this in a real turbine or a full-scale turbine. And the other thing is that it's not, this is something you would only really consider for a turbine that you really expect that you will have some sort of problem with. So either because you're running at loads that the machine is not really designed for, and you have issues with resonance occurring at the blades, or you have a turbine which incidentally, as I said, developed problems with vortex shedding and vortex induced resonance over time, and so you wanted to fix that issue. So it would have to be or beneficially, it would have to be a turbine which already had a problem, and then you could see how much would this solution improve the running of the machine. And there's also, of course, the necessary downside that when you introduce surface changes in the topology of the foil itself, you will expect to have some level of pressure loss, meaning you would get a small reduction in the peak efficiency of the turbine. And this is kind of the cost of running flexibly. So again, you have to kind of choose, do you want peak efficiency or do you want a turbine that can operate across a lot of different loads and kind of do this safely?
There's a question from Petter Østby. I think you should be able to talk now, Petter.
Hi, Christian. Thank you for a very nice presentation.
Hi. Yeah.
So this serrated edge was not successful in your experiment. Do you think there is another? Could you design it differently, like with the spacing or angles, so that it would be working as intended?
It's possible, but the main motivation for testing the vortex generators was to provide a control for the physical principles. As you know, the vortex generators, they are located upstream of the separation line. And this provides the control that we need to check if this really does make a difference or not, because you could provide 15 different designs for the serrations, and all of them would provide slightly different results, most likely, judging from what we see in the literature with respect to how serrations affect the overall pressure fluctuations and sound, which is not at resonance conditions. You could change the serrations and this would kind of give you different results. But it seems like the main takeaway here is that for any type of serration, So assuming that you really do cut into the blade itself and thereby you increase the cross-sectional area at the root of the serrations themselves, then at resonance conditions, the flow field will be affected to such a degree that it can overpower the effect that the serrations themselves under off or lock-off conditions would have. So this means that I suspect that most type of serrations will not work during resonance conditions.
Okay.
But there are, so that's a long way to get to an answer to your question. But there are other ways of designing it so that you could kind of provide a hybrid. So you could kind of start cutting into the blades upstream of the separation line and not go all the way through, for example. So technically, this is not a serrated trailing edge anymore, but I think especially you will understand what I'm getting at here. And so yeah, that's what kind of gives me or gets me excited, because I see a path to a solution here.
Okay, very good. Thank you.
Anybody else wants to get a chance to ask Christian while he's here with us?
Yeah, I guess does that bode well for the well or bad for the clarity of the presentation?
Yeah,
I don't know. I hope it wasn't too technical, and that yeah, people got something out of it. And like I said, I'm available to discuss if anyone is interested. Yeah, for the researchers out there, of course, also the paper is available. So
it was very interesting, even for me, who is a civil engineer. So
okay,
you explained the problematics and the way out of it well.
great, thanks.
Okay, then if there are no other questions, I think we can finish early today. And, thank you everybody for your attention, and thank you very much, Christian, for presenting.
Yeah, no, thank you for listening again.
And have a nice rest of the Friday and nice weekend when it comes. Thank you.
Thank you.